In the early years of the Second World War, fighter pilots were asked to perform a task that bordered on the impossible. At speeds that often exceeded 400 miles per hour, in machines made of aluminum and steel, they were expected to hit another aircraft that was twisting, diving, rolling, and accelerating through the sky. It wasn't just a matter of pointing the nose and pulling the trigger. A pilot had to solve a moving geometry problem in his head, instantly. Imagine two aircraft closing toward each other at a combined speed of nearly 700 miles per hour. At that speed, the distance between them shrinks by almost 1,000 feet every second. The target is not stationary. It is turning, climbing, and changing direction constantly. The bullets fired from a fighter's machine guns take time to travel through the air, and during that short flight, the enemy aircraft will have already moved dozens of meters from where it was when the trigger was pulled. To score a hit, a pilot must aim not where the enemy plane is, but where it will be a fraction of a second later. This concept is called deflection shooting. It sounds simple in theory, but in the chaos of combat, it becomes incredibly difficult. The pilot must estimate the enemy's speed, direction, and distance, all while flying his own aircraft, watching for other enemies, and avoiding being shot down himself. Every turn changes the geometry. Every second changes the distance. During the war, most fighter aircraft relied on what was known as a reflector gunsight. The system was mechanically simple. A small illuminated reticle, a glowing aiming mark, was projected onto a glass plate in front of the pilot. When the pilot looked through the glass, the reticle appeared to float in the sky ahead of the aircraft. Wherever the reticle pointed, the guns were aligned. But the sight did not calculate anything. It gave the pilot a reference point, nothing more. The rest of the work had to be done in the pilot's mind. A Luftwaffe fighter pilot flying a Messerschmitt Bf 109, for example, had to estimate how far away his target was. He had to judge the angle of the enemy's turn. Then he had to aim ahead of the aircraft, sometimes several plane lengths ahead, so that his stream of bullets would intersect the enemy's future path. If he guessed wrong by even a small margin, the bullets would pass harmlessly behind or in front of the target. Combat reports from the war showed just how difficult this was. In many air battles, pilots fired hundreds, sometimes thousands of rounds without scoring a single hit. Even experienced pilots often needed to close within a few hundred meters before they dared to open fire. At longer distances, the chances of hitting anything dropped dramatically. And yet, those few seconds of firing were often the only opportunity a pilot would get. World War II dogfights were fast and violent encounters. Two fighters might spiral toward each other in a turning battle, each pilot trying to get onto the other's tail. The goal was simple: reach a position behind the enemy aircraft where your guns could fire, while his could not. But achieving that position required skill, energy management, and constant awareness of speed and altitude. Once a pilot managed to line up a shot, he had only a brief window to act. The target might remain in the gun sight for 1 or 2 seconds before the geometry changed again. In that tiny slice of time, the pilot had to judge the range, estimate the correct lead angle, stabilize the aircraft, and fire. Under those conditions, accuracy depended heavily on instinct and experience. Veteran pilots developed a kind of mental library of angles and distances. They learned, through hundreds of hours in the air, how far ahead of a turning fighter they needed to aim. Some described it as a form of intuition. They no longer calculated consciously, they simply felt where the bullets needed to go. But intuition could only go so far. As the air war intensified over Europe, the limitations of traditional gun sights became increasingly clear. Pilots were flying faster aircraft than ever before. Fighters like the P-51 Mustang, the Focke-Wulf 19, and the Messerschmitt 110 could exceed 400 miles per hour in level flight. Closing speeds in combat were rising, and the time available to aim was shrinking. Military analysts studying combat data began to notice something troubling. Even highly trained fighter pilots were missing far more often than they were hitting. Some studies suggested that only a small percentage of bullets fired in air combat actually struck their targets. Vast amounts of ammunition were being expended for relatively few confirmed kills. This wasn't just a tactical problem, it was a strategic one. Air forces depended on fighter aircraft to defend bombers, intercept enemy raids, and control the skies over battlefields. If pilots could not reliably hit their targets, the effectiveness of entire air campaigns was reduced. The problem of aiming had quietly become one of the most important technological challenges of the war. Engineers and scientists in several countries began searching for a solution. What if the gunsight could do the calculations automatically? What if the pilot no longer had to estimate the lead angle himself? The idea seemed almost futuristic. To make it work, a device would have to measure the movement of the aircraft during a turn and use that information to predict where the enemy plane would be in the next fraction of a second. It would then need to move the aiming mark accordingly, showing the pilot exactly where to fire. In other words, the gunsight would have to think. For years, this remained more of a theory than a practical system. Aircraft cockpits were cramped, vibrations were constant, and any equipment installed in a fighter had to be extremely reliable. A complex calculating mechanism inside a tiny optical sight sounded like a recipe for mechanical failure. But the pressure to improve aerial accuracy continued to grow. By the middle of the war, thousands of aircraft were fighting daily over Europe. Massive bomber formations crossed the continent under heavy escort, while intercepting fighters climbed to meet them. In these crowded skies, a pilot's ability to land the first accurate burst of gunfire determined whether he survived the encounter. Every major air force understood the stakes. German engineers worked to improve their own reflector sights. British scientists experimented with new optical systems. American engineers began exploring an entirely different concept, one that involved gyroscopes, moving reticles, and automatic prediction. At first, few pilots realized that a quiet technological race was underway. To them, the challenge remained the same as it had always been: get close, aim carefully, and hope your instinct was good enough. But somewhere in a laboratory and workshop far from the front lines, engineers were building a device that promised to remove guesswork from aerial combat entirely. If it worked, it would change the way fighter pilots aimed forever. And when it finally appeared in the cockpit of an American fighter aircraft, the balance of the air war would begin to shift in ways few people immediately understood. By 1943, the air war over Europe had become a contest not only of pilots and aircraft, but of engineering. Every nation fighting in the skies understood that speed, firepower, and maneuverability mattered. But quietly, behind the scenes, a different realization was taking shape among scientists and military planners. Even the best fighter aircraft in the world meant little if its pilot could not reliably hit the enemy. For years, pilots had relied on skill and intuition to aim their guns. The reflector gun sight placed a glowing aiming mark in front of the pilot, but it did nothing to solve the hardest part of the problem, the calculation of lead. If the enemy aircraft was turning, climbing, or diving, the pilot had to guess how far ahead to aim so that the bullets and the target would meet in the same point in space. The faster aircraft became, the harder this calculation was. By the middle of the war, many fighters were closing on each other at speeds approaching 700 miles per hour. At those speeds, even a tiny error in judgment meant a complete miss. Pilots often fired long bursts of ammunition with little result. American engineers studying combat reports began to look at the problem differently. Instead of asking pilots to become better mathematicians in the air, they asked a simple question: what if the machine could do the math instead? This idea led to one of the most remarkable innovations of the war, the gyroscopic gunsight. Unlike traditional reflector sights, this new device was designed to measure the movement of the aircraft itself.
Inside the unit was a small but extremely precise gyroscope, a spinning mechanism capable of detecting how quickly the fighter was turning. When an aircraft entered a turn, the gyroscope sensed the rate of rotation and fed that information into the sight's mechanical system. At the same time, the pilot adjusted a control based on the wingspan of the enemy aircraft he was attacking. By matching the target's wings to marks inside the sight, he could estimate the distance to the target. With both pieces of information, the rate of turn and the approximate range, the gun sight could automatically calculate the correct lead angle. Instead of aiming directly at the enemy aircraft, the pilot simply placed the moving reticle where the sight told him to. The device shifted the aiming mark ahead of the target by exactly the amount needed for the bullets to intersect its path. In other words, the gun sight predicted the future position of the enemy aircraft. The American version of this system became known as the K-14 Gyroscopic Gunsight. At first glance, it looked similar to earlier reflector sights, but inside it was far more sophisticated. Tiny mechanical linkages translated the movement of the gyroscope into motion of the reticle projected onto the glass in front of the pilot. When the fighter began to turn, the reticle would drift away from the center of the sight. The faster the turn, the greater the movement. To an inexperienced observer, it might have looked strange, the aiming mark sliding across the glass, but to a trained pilot, it represented something extraordinary, a constantly updated firing solution. Of course, technology alone was not enough. Pilots had to learn a new way of shooting. Instead of trying to guess the correct lead themselves, they were taught to trust the sight. Training manuals instructed pilots to track the enemy aircraft smoothly, keeping it centered in the sight while adjusting the range control. Once the wingspan of the target matched the markings in the sight, the reticle automatically indicated where to fire. The system dramatically simplified the mental workload of the pilot. Instead of performing complex calculations under extreme stress, he could focus on flying his aircraft and maintaining a stable tracking position. Early tests showed remarkable improvements. Pilots using the gyroscopic sight were able to hit targets at greater distances and during more aggressive turning maneuvers. Situations that previously required perfect timing and instinct now became far more forgiving. When the system began appearing in operational units, it was installed in some of the most famous American fighters of the war, including the P-51 Mustang and the P-47 Thunderbolt. These aircraft were already among the best long-range fighters in the world. Now they had a technological advantage that many of their opponents did not even know existed. At first, the new sight did not attract much attention outside of pilot circles. To ground observers or enemy intelligence, it looked like just another cockpit instrument, but in the air, its effect could be dramatic. A pilot who once needed to close dangerously near to his target could now fire accurately from farther away. A fleeting 1-second firing opportunity became enough time to land effective hits. Even less experienced pilots found themselves scoring victories more often than before. American pilots noticed the difference immediately. Many described the sensation of using the sight as almost unfair. Instead of guessing where to aim, the answer appeared directly in front of them, floating in the air as a glowing reticle. One American pilot later explained it in simple terms. Before the gyroscopic sight, shooting down an enemy fighter required instinct and a bit of luck. With the new system, it felt as if the aircraft itself was helping you aim. But the existence of this technology was not widely known beyond Allied forces. German and Japanese pilots continued to rely primarily on traditional reflector sights, trusting their experience and reflexes. For a time, this quiet advantage remained hidden inside the cockpits of American fighters flying escort missions over Europe. Day after day, formations of P-51 Mustangs accompanied bombers deep into German airspace, engaging enemy fighters in fierce aerial battles. To the German pilots facing them, the encounters must have seemed puzzling at times. Allied fighters appeared to land accurate bursts of gunfire from angles and distances that previously would have been extremely difficult. But the reason for this improved accuracy was not immediately obvious. The secret remained locked inside a small metal box mounted just in front of the pilot's eyes, a device filled with spinning gyroscopes and delicate mechanisms silently solving complex equations every second of the flight. And for a while, that secret stayed on the Allied side of the war, until one day in 1944, when a damaged American fighter fell from the sky and landed on territory controlled by Germany. Inside its cockpit was an intact gun sight unlike anything Luftwaffe engineers had ever seen.
By 1944, the air war over Europe had reached a level of intensity few could have imagined only a few years earlier. Every day, hundreds of aircraft filled the skies above Germany and the occupied territories. Massive bomber formations pushed deeper into the Reich, escorted by long-range fighters determined to keep enemy interceptors away. The battles were relentless, chaotic, and often brutal. Aircraft collided, engines failed, and damaged fighters spiraled toward the ground across fields, forests, and small towns scattered across the continent. Whenever an enemy aircraft crashed inside German territory, it immediately became a target of interest. Military patrols and technical teams were often dispatched quickly to inspect the wreckage. These teams were not just looking for bodies or documents, they were hunting for technology. By this stage of the war, every piece of equipment recovered from an enemy aircraft was valuable. A new radio component, a navigation device, or even fragments of armor plating could reveal something about the capabilities of Allied aircraft. German engineers had already learned much from captured equipment earlier in the war. But most crashes left very little intact. Fighters hitting the ground at high speed rarely preserved delicate cockpit instruments. Then, sometime in 1944, one crash site delivered something unusual. An American fighter had gone down behind German lines. The aircraft had been badly damaged, but the cockpit had not been completely destroyed. When technicians began examining the wreckage, they noticed a gun sight mounted in front of the pilot's seat that looked slightly different from the ones they were familiar with. At first glance, it resembled a typical reflector sight, but when engineers removed it from the wreckage and examined it more closely, they realized that it was far more complicated than expected. The housing was heavier than normal, and inside the device were components that suggested a far more sophisticated mechanism. The sight was carefully transported to a technical evaluation facility, where German specialists began the process of dismantling it. As they opened the casing, they discovered something remarkable. Inside the compact metal housing was a precise mechanical system built around a gyroscope. The device was not simply projecting an aiming mark onto a glass plate, it was actively calculating the lead required to hit a moving aircraft. For German engineers who had spent years working with traditional reflector sights, the discovery was both fascinating and unsettling. The mechanism inside the sight used the motion of the aircraft itself to generate information. As the fighter turned, the gyroscope sensed the rate of rotation. Through a network of gears and linkages, this movement shifted the position of the reticle projected in the pilot's view. The faster the turn, the further the reticle moved from the center of the sight. Combined with the pilot's estimate of the target's range, the system effectively predicted where the enemy aircraft would be when the bullets arrived. In other words, the device was performing the deflection calculation automatically. For years, German fighter pilots had been forced to perform that calculation themselves in the middle of combat. They relied on experience, instinct, and countless hours of training. Now the engineers were looking at a device that removed much of that burden from the pilot entirely. One engineer reportedly remarked that the Americans had managed to build a mechanical brain for aerial gunnery. As the examination continued, the realization slowly spread among the technical staff studying the device. If this gun sight was being used widely by Allied fighters, it meant that American pilots had a significant advantage during turning dogfights. The device they had recovered was the K-14 Gyroscopic Gunsight, one of the most advanced aerial targeting systems developed during the war.
German intelligence teams had previously encountered rumors that the Allies were experimenting with improved gun sights, but few had imagined quite a system like this. The level of precision packed into such a small instrument was impressive. Tiny gyroscopes, carefully balanced components, and finely machined linkages worked together to produce a constantly shifting aiming solution. For the engineers studying it, the implications were obvious. If a pilot could simply track the enemy aircraft and allow the sight to calculate the lead automatically, his chances of scoring hits would increase dramatically. But there was another problem. It was already 1944. By this stage of the war, Germany was fighting a defensive battle on multiple fronts. Industrial facilities were under constant bombing. Resources were becoming scarce. Even when engineers developed new technologies, turning those designs into mass-produced equipment had become increasingly difficult. Still, the captured gun sight represented an opportunity. German scientists and technicians began carefully documenting every component inside the device. Measurements were taken, sketches were drawn, and the mechanism was studied piece by piece. Their goal was simple: understand how it works and then attempt to reproduce it. Reverse engineering the sight would not be easy. Precision gyroscopes required extremely careful manufacturing. The internal mechanisms had to be balanced perfectly, or the calculations would be inaccurate. Even small errors could render the entire system useless. But the potential reward was enormous. If the Luftwaffe could equip its own fighters with a similar sight, German pilots might gain the same advantage that American pilots now enjoyed. In the tight, twisting engagements of a dogfight, even a slight improvement in accuracy could decide who survived and who did not. For a brief moment, hope returned to the laboratory studying the captured device. Engineers began working on adapting the concept for German fighter aircraft. They explored how the mechanism could be integrated into existing cockpits and how pilots could be trained to use the new aiming method. Yet there was an uncomfortable truth that everyone involved understood, even if few said it out loud. Technology takes time. Designing a system is one thing. Producing thousands of reliable units, installing them in operational aircraft, and training pilots to use them effectively is another challenge entirely. And by the middle of 1944, time was the one resource Germany no longer had. The Allies were advancing on the ground, their bombers were dominating the skies, and the Luftwaffe was struggling to replace lost aircraft and experienced pilots. Still, the engineers continued their work, because somewhere in that captured American gun sight was a glimpse of what aerial combat was becoming, a future where machines could calculate faster than human minds, and where a small instrument in a cockpit could quietly decide the outcome of a battle in the sky. By the time German engineers finished studying the captured American gun sight, one fact had become impossible to ignore. The device was not a simple improvement. It represented a completely different approach to aerial gunnery. Instead of relying on the pilot's instinct, it turned the aircraft itself into part of the calculation. But understanding a technology and reproducing it were two very different challenges. Once the internal mechanisms of the captured sight had been carefully documented, German engineers began discussing how such a system might be adapted for their own fighter aircraft. The Luftwaffe still fielded some of the most capable fighters of the war, including the Messerschmitt Bf-109 and the Focke-Wulf FW-190. Both aircraft were fast, heavily armed, and extremely dangerous in the hands of experienced pilots. If they could be equipped with a comparable gyroscopic gun sight, German pilots might regain some of the advantage they had lost in the skies over Europe. But by 1944, Germany's aviation industry was operating under conditions that made innovation extremely difficult. Factories that once produced aircraft and precision instruments were now frequent targets of Allied bombing raids. Production lines were disrupted, skilled workers were being drafted into military service, and raw materials were becoming increasingly scarce. Even maintaining existing aircraft had become a challenge in many Luftwaffe units. Despite these obstacles, research teams began exploring ways to develop their own version of the gyroscopic gunsight. The captured device provided a valuable starting point, but reproducing it required extremely precise engineering. The heart of the system was the gyroscope itself, a small spinning rotor capable of detecting minute changes in rotational movement. Building gyroscopes with the required accuracy demanded advanced machining techniques and carefully balanced components. German engineers had experience with gyroscopic instruments in navigation systems and autopilots, but integrating such technology into a compact, durable gun sight presented new challenges. The device had to survive vibration, rapid acceleration, and the harsh environment inside a fighter cockpit. It also had to remain reliable during high-speed maneuvers that placed enormous stress on the aircraft. Beyond the mechanical difficulties, there was another question. How would pilots actually use the system? Traditional reflector sights required little explanation. A pilot simply placed the glowing reticle over the target and fired, adjusting his aim based on experience. A gyroscopic gun sight, however, behaved differently. The reticle moved depending on the aircraft's motion, and the pilot had to understand how to interpret that movement. Training programs would need to be created, manuals written, and instructors prepared to teach the new method of aiming. In a time when experienced pilots were already in short supply, adding a new training requirement was not a simple decision. Still, the potential advantages were too significant to ignore. Experiments began to determine how such a sight might be installed in operational fighters. Engineers looked at cockpit layouts in aircraft like the Messerschmitt Bf-109 and the Focke-Wulf FW-190, studying where the device could be mounted without interfering with other instruments. Electrical systems needed to be adapted to power the sight, and controls had to be designed so the pilot could adjust the range based on the wingspan of the target aircraft. Prototype installations were discussed, and limited development work moved forward. But the environment surrounding these efforts was growing more desperate with each passing month. By late 1944, the Luftwaffe faced severe shortages of both aircraft and trained pilots. Fuel supplies were dwindling, making it difficult for units to conduct even basic training flights. Many new pilots were being rushed into combat with only minimal preparation. Under these conditions, introducing a sophisticated new gun sight system was an enormous logistical challenge. Even if the technology could be successfully copied, producing it in large numbers required factories, materials, and time. All three were becoming increasingly scarce. Meanwhile, Allied aircraft continued to appear over German territory in ever larger numbers. Bombing raids targeted industrial centers, railways, and airfields. Every new production program had to compete with urgent demands for replacement aircraft, engines, and weapons. Some engineers continued pushing forward, believing that even a limited number of improved gun sights might help German pilots defend their airspace more effectively. Others understood that the war had already moved beyond the point where a single technological innovation could reverse the situation. Still, the concept itself left a lasting impression on those who studied it. The captured gun sight demonstrated something important about the future of aerial combat. Human reflexes and intuition had limits. Machines, however, could process motion and geometry far faster than the human brain. A device that could automatically calculate the correct lead angle represented the beginning of a new relationship between pilot and technology. Instead of relying entirely on instinct, pilots would increasingly depend on instruments that enhance their awareness and precision. In many ways, the gyroscopic gun sight was an early step toward computerized targeting systems that modern fighter aircraft would one day carry. But for Germany in 1944, the reality was far less optimistic. Even as engineers experimented with the concept, the situation in the skies over Europe continued to deteriorate. Allied fighters now roamed deep into German airspace, escorting bombers and hunting interceptors. The numerical advantage was overwhelming, and the Luftwaffe was slowly being worn down. New aircraft designs, advanced weapons, and experimental systems continued to appear in small numbers, but none of them could be produced fast enough to change the course of the war. The captured American gunsight had revealed a glimpse of the future. It showed how technology could simplify one of the most difficult tasks in aerial combat. But by the time German engineers understood its significance, the war was already entering its final phase. And somewhere in the skies over Western Germany, pilots were still fighting desperate battles, unaware that a tiny instrument in the cockpit, no larger than a small metal box, had quietly reshaped the mathematics of the dogfight.
By late 1944, the skies over Western Europe had become one of the most dangerous places on Earth. The air war had reached a level of intensity that few could have imagined when the conflict began. Every day, hundreds of aircraft crossed the skies above Germany. Allied bombers moved in massive formations toward industrial targets, while fighter escorts swept ahead of them, searching for any German aircraft that dared to intercept. For the pilots of the Luftwaffe, the situation had become increasingly desperate. Earlier in the war, German fighter units had dominated the skies over Europe with experienced pilots and advanced aircraft. But by the final years of the conflict, the balance had shifted dramatically. Allied air forces now possessed overwhelming numbers, longer-range fighters, and a steady flow of trained pilots. Yet the German fighter pilots who remained were still highly skilled and determined. Many of them had survived years of combat and had developed exceptional instincts in aerial combat. They knew how to maneuver their aircraft to gain an advantage, how to exploit a moment of weakness in an opponent, and how to turn a brief firing opportunity into a deadly burst of gunfire. Somewhere within this chaotic air war, the technology captured months earlier was slowly influencing German thinking. Engineers and technicians had studied the American Gyroscopic Gunsight in great detail. Even if large-scale production proved difficult, the discovery had confirmed something important: aerial gunnery was changing. The future belonged to systems that could calculate faster than the human mind. Meanwhile, the fighting continued over regions like the Rhine Valley, where Allied bombers often passed on their way to targets deep inside Germany. The river and its surrounding cities had become a major corridor for air operations. Intercepting fighters frequently met escorting aircraft there, and the skies above the region often erupted into violent dogfights. These encounters were fast, confusing, and brutally short. A typical engagement might begin when radar stations detected incoming bombers approaching German airspace. Fighter units would scramble from nearby airfields, climbing quickly to intercept the formation. As they approached, they often encountered American escort fighters, especially long-range aircraft like the P-51 Mustang, whose job was to prevent German fighters from reaching the bombers. What followed was a swirling battle of speed, altitude, and timing. Fighters dived, climbed, and turned through layers of cloud and sunlight, each pilot searching for a brief moment when an enemy aircraft crossed his gun sight. In many cases, the entire encounter lasted only a few minutes. A pilot might see the enemy for a split second, fire a short burst, and then disappear into the sky again as the formation scattered. This was the environment where aiming technology truly mattered. Even the most experienced pilot could only make rough estimates in such conditions. When aircraft were turning violently and moving at hundreds of miles per hour, the difference between a hit and a miss could be measured in fractions of a second. A gunsight that could automatically calculate the lead angle gave its user a significant advantage. By this stage of the war, many American fighters were already equipped with the gyroscopic gunsight that engineers had worked so hard to develop.
Pilots flying escort missions trusted the system to guide their aim during those brief firing opportunities. Instead of guessing how far ahead to shoot, they could focus on tracking their target smoothly while the sight adjusted the reticle. In the chaos of combat, that small difference could mean everything. For German pilots, however, the situation was far more difficult. Even though their engineers had discovered the secret behind the American sight, the reality of war meant that the technology could not be deployed quickly enough to transform the Luftwaffe's capabilities. Aircraft shortages, fuel problems, and constant bombing raids had placed enormous pressure on Germany's aviation industry. The innovation had arrived too late. The battles over the Rhine and other parts of Western Germany continued day after day as Allied forces advanced toward the German border. Each engagement was another test of skill, nerve, and luck. Pilots who survived these encounters often described them as moments of pure intensity, seconds where every movement of the aircraft mattered. Some fighters returned to their bases riddled with bullet holes. Others never returned at all. In the end, the captured gunsight became less important as a weapon than as a symbol of a turning point in military technology. It showed how the nature of combat was beginning to shift. Instead of relying entirely on human judgment in the heat of battle, machines were beginning to assist pilots by processing information faster than the human brain could manage. The gyroscopic gunsight did not win the war by itself. Victory in the air depended on many factors: aircraft production, pilot training, fuel supplies, and strategic planning. But the small piece of engineering quietly demonstrated how a small device could dramatically improve a pilot's chances in combat. After the war, the lessons learned from systems like the K-14 Gunsight would influence the design of nearly every modern fighter aircraft. As technology advanced, mechanical calculators would eventually give way to electronic systems and digital computers capable of performing far more complex calculations. Modern fighter jets now use radar, sensors, and advanced targeting computers to track enemy aircraft automatically. Missiles can predict interception paths with extraordinary precision, and helmet-mounted displays can show pilots exactly where to aim simply by turning their heads. But the roots of that technology can be traced back to a much simpler device, a small gyroscopic mechanism mounted in the cockpit of a World War II fighter, a device that quietly solved the geometry of the dogfight. And for a brief moment in 1944, when German engineers opened the casing of a captured American gunsight and saw the spinning gyroscope inside, they realized they were looking at the future of aerial warfare. By the time they understood it, however, the war that might have been changed by such an invention was already slipping beyond their reach.